In this video, I'm going to continue on with some applications of the cross product. So one of the big examples or applications of the cross product is torque. And torque is the action of a force that causes an object to turn rather than change position. So some examples, you might be able to think of these, but tightening or loosening a nut using a wrench. There's a tool called a torque wrench. You can also see it in the force to a bike pedal to make a crank arm rotate. And then the last example that we'll note here, opening a door by pushing or pulling. And maybe you can think of some more examples of torque in your everyday life. There are lots. So some terms that you need to be aware of is that there's an applied force here at the end of the wrench. There is a lever arm, which makes it easier to tighten or loosen the bolt in the example that we're looking at here. And then right here, we have our axis of rotation. So here's another example. We have our radius and our force. And our force here. So we've got our radius and then our force, which is actually tangent to the circle that's created. So what we have here is we can use the cross product to figure that out. We have T to represent torque is R cross F, or RF sine theta in the direction of the normal. So F is the applied force. R is the vector determined by the lever arc, acting from the axis of rotation. Theta is the angle between the force and the lever arm. N is just a direction. It's a unit vector that is perpendicular to both R and F. So let's put that into practice. So we have a 20 Newton force is applied at the end of a wrench that is 40 centimeters in length. So this is going to be our R. The force is applied at an angle of 60 degrees to the wrench. Calculate the magnitude of the torque about the point of rotation, M. So let's take a look at our equation to find the torque. We have the magnitude of the torque is equal to the magnitude of R times the magnitude of F times the sine of the angle between them. Now, a couple of things that we need to consider is that this equation is going to ask for you to change R into meters. Always, in order to use the equation, R has to be in meters. So, easy enough conversion here. We're going to multiply by the magnitude of our force. And then we're going to times by the sine of the angle between them, also given to us in the question. When we multiply all those together, we get about 6.93 joules. And so that tells us that the magnitude of the torque is 6.93 joules. So let's take a look at another example of the cross product and torque. So here we're going to take a look at the torque produced by a cyclist exerting a force of 115 newtons on a pedal in the position shown in the diagram if the shaft of the pedal is 16 centimeters long. So let's add in some things on our diagram here. So we've got, hopefully you can understand this picture. We've got the horizontal, here. This would be the axis of rotation where all the gears meet in the bicycle, this part here. And this part here is the pedal, okay? So we're gonna add in, this arrow represents our force here, applied by the rider. And I'm going to tell you that this angle is 15 degrees. Here is where we have our radius. Now, hopefully you've noticed a problem in that our vectors are not tail to tail right now. They're actually head to head. In order to figure out the angle between them so that we can find the magnitude of the torque, we're going to have to do some shifting of the vectors to figure out the angle between them. So the way that I like to think of this one is I'm going to slide my vector sort of along the pedal like this. So hopefully you can see I've got the same magnitude with this new red arrow that I've drawn, but now I've got the tip of my force vector meeting with the tail of my radius vector. So now I'm going to do the same thing to the force vector. And let's use a brighter color. Let's use orange. So now I'm going to take my force vector and I'm going to slide it down, so along the same line. Hopefully you can see it's meant to be the same magnitude, but now I've got two vectors that are tail to tail, and I'm going to find the angle in between them so that I can use the formula for the torque. So let's redraw that up here. So I've got my radius vector here. I've got my force vector here. Now I've got them tail to tail. So now what angles do I know? I've got my vertical and I've got my horizontal. Let's add one more thing to our diagram here. So our angle between the radius and the horizontal is 25 degrees. I'm just telling you that. You can't find it. It just wasn't drawn on the diagram. Okay. So let's start by putting in the angle between the radius and the horizontal. That's 25 degrees. And I know that my angle in between the force and the vertical has to be 15 degrees. So what I'm looking for is this whole angle here. Let's do that in green. So the angle between the radius and the force. So hopefully you can see the combination here. I'm going to start at 90 and I'm going to take away 15 because that's going to give me this part of my angle. And then I'm going to add 25 to find that my angle between the two is 100 degrees. So now I can use my formula to find the magnitude of the torque. So I've got the magnitude of the torque is equal to the magnitude of the radius times the magnitude of the applied force, sine of the angle between them. So I'll put in my known values. So I've got the shaft of the pedal is 16 centimeters long. So remember, we need to change that into meters. My applied force is 115 newtons. And then the sine of the angle in between them, where the angle is 100 degrees. And when I multiply all that out, I'm going to get approximately 18.1 joules. So the magnitude of the torque vector is 18.1 joules. And since we're just asked to find the vector, we need the direction as well. So that means that we have to take a look at our right-hand rule. So if you point your fingers in the direction of R of your right hand and you curl them towards F, you're going to get your thumb pointing into the page. Make sure you're using your right hand to do the direction. This is another example of how to find the torque. One thing, we found the angle 1 one way back up here just before we finish the video. There are lots of other ways to come across this angle. This is how I find it easiest to visualize, by sliding the vectors to make them tail to tail. Okay, so good luck. This is one application of the cross product between vectors.